right, and this is the second lesson in Unit 7, working with series. Make sure you watch Lesson 1 if you were not here in class for that, because you need to know about sequences in order to move on to series. And a special shout out to all of you sophomores who were not in class today because you were at the Air and Space Museum. I hope you got to ride the simulators in the back. I did that once. I'm pretty sure I crashed a plane. So hopefully you did a better job than I did. Anyways, moving on. Okay, so series. A series is the sum of the numbers of a sequence. So now we're taking that pattern, we're adding up all of our terms. And of course, there is a formula that can help us because I could ask you to add 4 terms, no big deal. But what if there's 100 numbers in the pattern? You don't want to have to sit there and type in those 4 numbers or the 100 numbers. So there are 4 new formulas that we're going to look at because if you remember before, I told you there were 8 total. 4 have to deal with sequences, and then 4 have to deal with series. And I'll make a quick short video going over the formula sheet as well, but make sure that if you don't have a copy, go to my website and download it and print it or just look at it, whatever, so you have those formulas in front of you. Okay, so an arithmetic series is the sum of an arithmetic sequence. Geometric series, sum of a geometric sequence. All right, so taking a look here says find the sum of the first 5 terms. So if you remember back to our sequence, our explicit pattern, this is our explicit formula. Here's the first number, 6, and our common difference is 4. So to find the next, or to find the first 5 numbers, I can add 4, and then I can add them all together. And when you type that in, you get 70. Okay, so just typing 6 plus 10 plus 14, etc. All right, and then to do it for geometric, first number is 1, ratio is 2. So 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. So go ahead and add those up. And you get 255. All right, not a big deal, but once again, what if I ask you to add a whole lot of terms? That could get annoying. So you can go through on your own time, and this kind of just explains where where the sum formulas come from, but let's take a look at these down here. So there's 2 different formulas that we can use to find the sum of an arithmetic series. It's Formula 1 or Formula 2. And it really does not matter, guys, which one you use. In any case, for the arithmetic ones, you could use either. It's just sometimes it'll be easier to use one versus the other. So let's take a look at the difference. So remember, n represents any given number in the pattern. So if I'm finding the sum, n this time is representing the last number, okay? The last number in my series. So if there's 10 numbers, I'm putting a 10 there for n. Okay, so that's how many numbers. This is the first number and this is the last number. So in order to use this formula, I need to know both the first and the last term. Now over here, I don't need to know the last term. I only need to know how many numbers are in my pattern, the first number, how many numbers are in my pattern, and the common difference. Okay, so it kind of just depends on the information that you're provided, which one will be the better formula to use in each situation. Now, if you don't know the last number, you can always find it using the explicit formula so that you could use the first formula here, but that might just be a little bit more work. All right, so let's actually take a look at this. So I wrote the 2 formulas on top again, so you don't have to keep going back and forth. My first example says find the sum of the integers from 1 through 1,000. So in this case, I know the first and the last term, so it's probably going to be easier to use the first formula. I can totally use this one too because I know the first number and it's saying the sum of the integers between, so I know my common difference is 1. So I could use either, but the first one's shorter, so let's go ahead with that. So I'm finding the sum of the first 1,000. Okay, so I've got 1,000 divided by 2. The first number is 1, the last one is 1,000. So now I'm just doing the math. I'm really just doing 500 times 1,001, right? Because that's, 500, add them together. So when I do that, I get 500,500. So that's the sum of my first 1,000 numbers in that pattern. And I'm done. Once again, I totally could have found that using the second formula, but I mean, yeah, I used the first one. All right, number 4 says the first number is 40. The difference is -3. What's the sum of the first 10 terms? So in this one, I know the common difference in the first number, so it's probably better to use the second formula. Now, you could totally use your explicit formula to find the last term so that you could use this formula, but it might be a little bit more work. It's up to you. Okay, so first 10 terms, so 10 is my n, so I'm doing 10 divided by 2 times 2 times my first pattern, which is 40, so 2 times 40. plus negative 3 times n minus 1, so 10 minus 1. And then just do the math. Okay, so when I do that, I have 5 times 80 minus 27. I got that by negative 3 times 9. So when all is said and done, 80 minus 27 times 5 gives me 265. Okay, so for an arithmetic series meaning it's finding the sum, it really doesn't matter which of the two formulas that you use. You can use either, okay? Just decide which one's better. All right, so this is a word problem, which is a continuation of, we did this, the beginning part A in our sequence notes. So it tells us we're putting money in a piggy bank. Each week we're adding $3 more than the previous week. The first week we put in $10. How much are we putting in during the 25th week? So for this, I need my sequence formula. It's not asking me for a total yet. It's asking me for what I put in. So we're going to use our arithmetic sequence explicit formula, which once again, it's on your formula sheet. So I'm finding what I'm putting in there during the 25th week. Okay, so I've got, I'm starting with week 1, I put in 10. My common difference is 3. And on week 25, what's going in there? So do your math, and it's 82. Okay, so $82 is what I'm putting in. Now I'm saying how much money will I have in the account? So now I'm asking for the total. Now this is turned into a series question. Okay, because it's saying take everything up until this point and add it together. That's me trying to write the word series. Okay, add it together. So we can use either version of our formula, but since I know the first number is 10, because that's what I put it on week 1, I know the last number is 82 because that's what I put on week 25, I'm just going to use that one. Okay, so it's going to be n over 2, so 12.5. I got that by doing the 25 divided by 2. Okay, 25 because that's how many weeks. First one is 10 plus 82 is the last week. Okay, so we're doing 12.5 times 92. And we get 1,150. Okay, so if you can keep this up, you're going to get, a good chunk of change in there, as long as you don't spend it. Okay, so for arithmetic series, does not matter which formula we use. Okay, let's take a look at geometric now. All right, now geometric has two different formulas we're going to look at also, but in this case, they do matter. Okay, we have our finite and our infinite. Okay, and that's finite, not finite. Finite means it ends. And then infinite will go on forever and ever. And we'll take a look at the infinite one shortly. But when you look at your formula sheet, you'll notice the second equation has an S with a little infinity symbol. That's how you know that's the one for an infinite series versus the one that just has the N is for your finite, meaning it ends. How do I know it ends? A, I could tell you, or B, if you notice in all of these patterns on this page, it ends. There's no blah, blah, blah. If it was an infinite series, I would have plus dot, dot, dot at the very end of it, indicating it's going on forever and ever and ever. Or I'm telling you it's an infinite. Okay. So for this formula, all you need to know is the first term, the ratio, and how many numbers are in the pattern. You don't need to know the last number, which is great. So in this example, it says find the sum of the first 12 powers of 3. So 3 to the first, 3 to the second, 3 to the third, etc. Okay, so finding the sum of the first 12, so S sub 12 equals the first number is 3 times 1 minus the ratio. Well, let's think about it. It's 3 to the first, 3 to the second, 3 to the third. So my ratio is 3 because I'm multiplying by one more power of 3 every time. And my n is 12. Okay, because there's 12 numbers in the pattern. Divided by 1 minus the ratio, which is 1 minus 3. Now, guys, when you're putting in this into your handy-dandy calculator, I want you to be careful here. If you're going to just type it in as is, you need to make sure that you put parentheses around the entire numerator first, and then do parentheses. Okay, if your ratio is a fraction, that will need parentheses as well. So it can get a little tricky entering this. Okay, notice it's the 3 that's raised to the power. I'm not doing 1 minus 3 first. So I have the parentheses around the entire numerator. And now I have parentheses around the entire denominator. Okay, another option would be to simplify first. Simplify your numerator, simplify your denominator, and then divide them. Another option would be if you hit alpha, go to y equals and hit enter, it brings up a fraction bar for you. So the nice thing about that is you don't need to worry about those extra parentheses around the entire numerator and denominator. So that's another option. It was alpha, y equals enter. Okay, I should get the same answer. So 7,907, 160. Okay. All right, so in number 8, same thing. We can find the sum of the first 10 terms. So I know this is a series, guys, because there's plus signs in between. A sequence would be a list and would just have commas. That's the difference when you're looking at it in this, you know, in written out form. A sequence has commas, a series has plus signs. And I'm going up to 10 terms because it's the last, it ends at a sub 10. So I'm finding some of the first 10 terms. First number is 15. My ratio is 1/5. How did I get that? I worked backwards and I divided. Okay, so since my ratio is a fraction, I need to put that in parentheses. It will just be an ugly mess if I don't. To the 10th power. Divided by 1 minus my ratio of 1/5. Okay, so I like using that fraction option, the alpha y equals enter. I think it makes it just a little bit easier. I have one less set of parentheses to worry about. But and then from here, if you want, you can even do alpha y equals again to get another fraction up for that ratio. Or you can just do 1 divided by 5 in parentheses at that point. Up to you. Sorry, up to the 12. Parentheses, down here is 1 minus fraction, 1 arrow over, 5th, arrow over, arrow out, enter. 8.75 if I round it. Okay, which makes sense because I'm starting at 15, but then I'm starting to add small fractions. So my sum should not get too huge. All right, for time's sake, we're going to skip 9, but feel free to try it on your own and check the answer key. One thing we'll notice is, or point out is, be careful. It is a series, but I'm noticing I'm going from subtracting to adding, subtracting to adding. So that tells me my ratio is going to be a negative. Okay, so just be careful with your signs, -1/2. All right, you can try that one on your own. All right, find the sum of the series. Okay, I'm giving you the last term. Well, I don't need the last term, but I do need to know my n, which I don't know what number that is in the pattern. So there's a couple different options we can do here. Now, what you could do is you could set up your explicit formula like we did before to find out what number in the pattern something is. So to find out whatever position it is, I can use my explicit. But with a geometric, it gets quirky. Let me show you. First number is 3. My ratio is times 2. To the n minus 1 equals 768. So if I said equal to that last number, I can solve to find out what it is, what the n is. But the problem with this is, guys, is we're trying to now solve for a variable and an exponent. In order to do that, we need to know how to solve for logs and stuff, log bases. We don't know how to do that yet, so this option isn't going to be an option for a geometric one. We can do it for an explicit, for an arithmetic, which I'll show you later. But in this case, if I'm asking you to find out how many terms are in a geometric series, you're going to have to list out the ones in between and count. I know it's not ideal, but I will never give you one that's too huge. All right, but if I list out all my numbers, I'm going 3, 6, 12, 24, 48. I'm counting on my finger, sorry. 96, 192. 192 times 2 is 384, 768. All right, so it's 3, 6, 12, 24, 48, 96, 192, 384. So there's 9 numbers, okay? If I listed out everything in between, this is the 9th number in my pattern. So once again, if I'm asking you to find out which number in a pattern for a geometric, you are going to have to list out the numbers in between and count, and I won't give you anything that's too big. All right, so now I can find the sum. The first number is 3 times 1 minus the ratio is 2 to the 9th power, because that's 9th term, all over 1 minus the ratio is 2. All right, so we go ahead and we do our math. Alpha y equals 1. I've got 3 times 1 minus 2 to the 9th. Down, 1 minus 2. Hit enter, and I have 1,533. That's my sum. At that point, if you list them all out, you could just add them together if you wanted to. Up to you. All right, we've got a word problem. So it says, according to George, blah, 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 blah. Let's get down to the gist of it. So it says that we're filling up a chessboard, okay? On the first square, it's 1 grain of rice. On the second, 2. On the third, fourth, whatever. So we're doubling the number of grains on each square. So there's 64 squares on the checkerboard. It goes 8 by 8. So how many grains of rice? So we're asking for the sum of the series. Our first number is 1. Our ratio is 2 because we're doubling. Sorry, sometimes I gotta look at my formula. Okay, 1 minus 2 to the 64th power, because that is my r, divided by 1 minus 2. Okay, so bring up my fraction. Alpha y equals 1. I've got 1 times 1 minus 2 to the 64th. One minus 2. It's going to give us a huge number. All right, so 1.84 times 10 to the 19th. When you see that E, it's telling you it's scientific notation. So it's 10 to the 19th. All right, that's really big. So then it says a grain of rice is approximately this many cubic centimeters. What's the volume? Right. Well, we already know each one has that itself as a volume. So now I'm just doing 0.03 times the 1.84 times 10 to the 19th. Okay, so kind of just taking that problem and extending it a smidge. So when I do that on my calculator, I can just say, okay, take that times 0.03. And we get 5.53 times 10 to the 17th. Which makes sense, it went down because it was less than 1. All right, so this is a formula we use for a finite and ending geometric series. You need to know the first term, the ratio, and how many numbers are in the pattern. If you don't know how many numbers are in the pattern, you've got to list them out and count. Sorry. Okay, let's skedaddle on. All right, we'll do sigma now, and then we'll do infinite at the end. Okay, so sigma notation is a Greek letter, sigma, and it means the word sum. So it's just another way of showing you to find me the sum, to evaluate a series using this. Okay, so this is what it says. Here's the rule, 3 times n plus 5, and this is your explicit arithmetic. It's just simplified. Okay, and it's saying find, so if I ask you to evaluate this, I'm asking you to find the sum of this pattern from the first term all the way up to the 1,000 terms. So you're adding 1,000 numbers together. Well, in order to do that, we simply need to know the formula. So you can use this formula where you find the common difference. And you find the common difference, the 3 is the common difference, and you plug this in, you plug 1 in to get the first number, or you can just find the first and the last term, which is what I like to do. So I'm finding the first term, so I'm plugging 1 in for 3. And when I do that math, I get 8. And then to find the last term, since I'm going up to 1,000 numbers, that's what I'm plugging in for n. And I get 3,005. So then I'm going to evaluate using that first sum formula. Now I know this is arithmetic because that's my arithmetic pattern. So when it's asking me to evaluate, I'm finding the sum of an arithmetic pattern. This is just another way to show it. So I need to use that sum formula. So I'm going to do n divided by 2, so 500, because that was the 1,000 divided by 2, times the first number plus the last number, so 3,013. Just added those together. Okay, so 3,013 times 500, 1,506,500. That's the sum. Okay, so once again, sigma is another way to show you to find the sum of a series. All right, now sometimes and you can go through and look at it. This is using the other formula, so you can check out that work. So if I might ask you to expand and find the sum. Expand means list out the terms. It tells us that right here. And then find the sum. So notice in this case, I'm not starting at the third term. I'm starting at 3 and I'm going up to 6. So I started by plugging 3 in. So 5 times 3, which gave me 15. Then 5 times 4, 5 times 5, 5 times 6. So I started by plugging in 3 and going up to 6. And it's saying expand and find. So here's the expanded form because it's all the 4 terms. And then I'm adding them together to get the sum. That's it. And then we're done. All right, so if I can write them out, here I'm starting at 4. So I'm doing 4 squared plus 5 squared plus 6 squared plus 7 squared. All right, and I'm stopping at 7 because that's the number on the top. So 16 plus 25 plus 36 plus 49. So my sum is 126. So once again, writing out means list out the pattern, the numbers, which I should write 16, 25, but for time's sake, you know that. All right, here, same thing, starting at 1, so 2 to the first plus 2 squared plus 2 to the third. So 2 plus 4 plus 8, 14. All right, so working backwards, we can now write it in summation notation. That is sigma. Summation notation is sigma. It's sum, right, in sum form. Okay, so now we're going to take this and make it look like this. So draw your sigma. You're always going to start at 1 because that's the first number in our pattern. So what number to put up top, you got to count. 1, 2, 3, 4, 5, 6, 7. So the 7 goes on top because that's how many numbers are in that pattern. And then the explicit formula needs to go here. Okay, the explicit formula in simplified form. So it's the first number times the common difference times n minus, I'm sorry, plus the common difference times n minus 1. So to simplify, I distribute, and I get 4n minus 4 plus the 3. So my explicit formula is 4n minus 1. So remember, when you're given something in this formula or format, it is explicit, but it's simplified. This is still your common difference, the coefficient of n, but you would have to plug 1 in there to find out what the first number is, okay, to find the 3. All right, over here, arithmetic again, because I notice I'm adding the same number each time. I noticed that over here. So putting it in sigma, so I'm starting at 1. I don't know how many numbers are in the pattern yet, so I can list them out, or I can solve for it because it's arithmetic. If it was geometric, I would have to list out in between and count my terms to find out how many are in there. But so let's write our explicit and find the n. We'll kill 2 birds with 1 stone. Okay, so 3 is my first number, times the common difference is 3, because I'm adding 3 every time, n minus 1. And I'm going to set this equal to the last number because that's going to help me figure out what term the last number is. All right, so if I simplify this first, let's get just the explicit part. So I have 3 plus 3n minus 3. So now when I simplify, I just have 3n. So that's the explicit formula simplified. Now when I put that equal to the 99, I can solve for what it is. Because remember, this is telling me which pattern, which term in the pattern that specific number is. Like if I put this equal to the 3, we know 3 is the first pattern. So look, when I solve, I divide both sides by 3 and I get 1. If I put it equal to the 6, divide both sides by 3 and I get 2. It's telling me 6 is the second number in the pattern. So when I divide both sides by 3, I get 33. So 99 is the 33rd number in the pattern. Why does that matter? Because that's how many numbers are in my pattern total, because that's the last term. So I can use the explicit to find out n for an arithmetic formula. I can't for geometric, and that's okay. All right, let's write sigma for this geometric one. N equals 1. Count 1, 2, 3, 4, 5, 6, 7, 8, 9. Write your explicit first number times the ratio, which is 2, to the n minus 1, and I'm done. That's it. Okay, you don't have to simplify like up here. Yes, I don't need the one that's relevant because 1 times anything is itself, but whatever. All right, over here, first number is 90. My ratio is 1/3. I'm multiplying by 1/3 to the n minus 1. Okay. First number, n equals 1. How many numbers are in my pattern? 1, 2, 3, 4, 5, 6, 7. There we go. Okay. All right, this next section I'm going to leave for you to practice on your own. Okay, all it's doing is evaluating. So you got to decide first if it's arithmetic or geometric and then evaluate. If it's arithmetic, you use your arithmetic sum formulas. If it's geometric, you use your finite geometric sum formula. Okay, I know they're all ending because this only has 10 numbers, this only has 9. That's supposed to be, just so you don't get confused, that's 9, I equals 1. And guys, you can use any letter down here, you don't need n. So that's just I, it's not imaginary, it's just an I to use an I. All right, so go ahead and practice those. Check your answers on the answer key. All right, we're going to go ahead and finish up with infinite geometric series. So an infinite geometric series is a series that's going on forever and ever and ever. There is no end. So once again, I pointed this out before. You could know because I could say, hey, it's infinite. If it was in sigma notation, it would have an infinity symbol. We'll look at that shortly. Or it could be a pattern that has dot, dot, dot at the end, meaning it's going on forever and ever. Now, our formula is pretty basic. So first of all, I know this is my infinite one because of the infinity symbol. I need the first term and I need the r. Now you'll see this notation back here. In this case, it really is important. The only way I can get a sum for an infinite geometric series is if it's what's called converging, which means the r is between -1 and 1. Because if the series is converging, it's approaching, getting closer and closer to 0. So that means that every new additional number that I'm adding on is so small, it's so close to 0 that it's really not making an impact on my overall sum. Okay, so I can find the sum there. If it's diverging, like in the movie, it's not approaching anything specific. So if my ratio is 2, every new number in my pattern, like if I start at 2, I've got 2 plus 4 plus 8 plus whatever, it's getting bigger, bigger, bigger. Every new number would make a huge impact on my total, so I can't find a sum because it's never ending. While versus this one up here, even though it's never ending, every new number is so small that it really is not making a difference. Let's take a look at that. Okay, so I've got a 2 by 2 square. So let's say the area of the square is 4. I'll 2 times 2 is 4. Let's not say it is. So let's say we painted just half of the square. How much would we paint? We're painting half of that. So half of 4 is 2. So if I painted half of the remaining area, so now I'm painting 1, okay, because it's 1 by 1. Now I'm painting half of the remaining area. That's 1/2, because I'm painting 1/2 by, it's going on forever. Hold on, look at me paint. Okay, now I'm painting half of that. Half this part. So that's 1/4 of the whole square. And we're painting half of the remaining area, 1/8. And we could keep going on forever and ever and ever. Technically, yes. Theoretically, no. There gets to a point where it's so small that, human error or whatever. But I can keep cutting this in half and half and half. And I should be able to keep going by halves. But eventually, it's going to get to such a small part that it's not going to look like I'm going to be able to have anything left to cut. If I keep breaking these numbers down, half of 1/8 is 1/16, 1/32, 1/64, 1/28, 1/256, 1/5, or 5, hold on, 512, 256 times 2, 512, 1/1024. So I keep going. Now, if I'm to add all of these up, eventually these numbers are so small, it won't make a difference. If I do 1 divided by 1024 on my calculator, I get a scientific notation. So I get 0.00097 blah, blah, blah. When I add that to 1, am I really making a difference? No. It's like I'm adding nothing. So while, yes, my series does also go on forever and ever, because it's getting so small, I can find a sum. I'm just using the major players. So if I were to express this as an infinite geometric series, it's 4 plus 2 plus 1 plus etc. Okay, and I can find the total. If I add up the numbers I have a 4 plus 2 plus 1 plus 1/2 plus 1/4 plus 1/8. And I could keep going, plus 0.0625 plus, etc. So I'm roughly getting, it's about 8 meters squared. It's just shy of it, okay? Because there's there's still, all of these up here are going to make a difference. All right, so it's about 8 meters squared. And I can do this by using that formula. It's the first number, let me switch color, sorry. It's the first number divided by 1 minus the ratio, which here my ratio is 1/2. I'm cutting it by 1/2. So when you actually evaluate that, you get 8. So once again, you can find the sum of an infinite series as long as it's converging, as long as the ratio is between -1 and +1, because it's getting so small. If it's diverging, you can't find the sum. So let's take a look down here. First, decide if it's converging or diverging. First, find the ratio. So the ratio here is -1/4, so it's converging. I can find the sum. So I'm doing the first number divided by 1 minus that ratio. Okay, so I can do that on my handy dandy calculator. Really, it's 1 divided by 5/4, because 1 minus a -1/4, and I get 0.8. Now it makes sense that the sum is smaller than the first term because notice I'm alternating positive, negative. So I am subtracting, taking some of the pieces away. That's my sum, that's my answer. This one over here, my ratio is times -2. So that's diverging. I can't find the sum, so I'm not going to do it because every new number makes such a huge impact that I can't say, hey, it's approaching this as a sum. I can't do it. Okay. Now I'm given my series in sigma notation. That doesn't matter. I can still evaluate it, okay? This is just written out as like a list. This is written out in sigma notation. First number is 10. Here's my ratio. That's converging. It's between -1 and +1, so I can use my formula. So I've got 10, my first number, divided by 1 minus -1/2. Okay? Type it in your calculator, and you get 6 2/3. Now notice, when I'm evaluating sigma, if it's an infinite series, I put an infinity symbol up top because it doesn't end. I don't put like 10 because there's not just 10 numbers in my pattern, there's an infinite amount. Over here it converges also because that's between -1 and 1. My first number is 15 divided by 1 minus 2/3. And this one's interesting. It's, it's a positive ratio, so my sum should be bigger. Over here, both of these were negatives, so my sum was smaller, but my sum here is 45. You might be like, what? That's so big. Well, think about it. 15, my second number is 10 because 15 times 2/3 is 10. And then, we're going on from there. So I'm getting some pretty big numbers to add up. So my sum is 45. All right, last 2 problems real quick, guys. You've been awesome hanging in there. I know this is long notes. So writing it using summation, same thing. Put your sigma, starting at 1, Since it's an infinite series, how do I know? There's dots. I'm putting an infinity symbol up top. And then we just write it using our explicit formula. Okay, I know it's geometric because I'm multiplying each time. So first term times the ratio. So I'm using my explicit formula here at -1. You didn't memorize it? No big deal. Go to your formula sheet. Over here, sigma, start at 1. First number in the pattern is 50. The ratio is 2/5. How did I get that? I worked backwards. I did 20 divided by 50 and got 2/5. Now, I'm not asking you to what's called, I can't think of the word right now. Evaluate, thank you, brain. I'm not asking you to evaluate, which would mean actually get the sum, which you could do though. Just plug your first term and your ratio into the formula. You didn't need to write the sigma to find the sum. It's just saying write it though. All right, so and even if it was diverging, you could still write it in sigma notation because I'm not asking you to evaluate. All right, so take a look, try the practice, bring your questions to me, especially if you were not here in class, okay? Adios.